What is the main motivation behind the proposed method LLM2Vec?
The main motivation behind the proposed method LLM2Vec is to transform any pre-trained decoder-only language model, LLM, into a universal text encoder for text embedding tasks. The method aims to address the architectural limitation of decoder-only LLMs, specifically their causal attention mechanism, which restricts token interactions and limits the ability to capture information across the entire input sequence. By enabling bidirectional attention, implementing masked next token prediction, MNTP, and applying unsupervised contrastive learning, CSSSE, LLM2Vec enhances the model's ability to produce rich contextualized token representations without the need for labeled data. The approach is highly data and parameter efficient, allowing for the efficient transformation of decoder-only LLMs into effective text encoders. Additionally, LLM2Vec leverages the advantages of decoder-only LLMs, such as learning from all input tokens during pre-training and excelling at instruction-following tasks, making it a valuable method for building universal text embedding models that generalize across various NLP tasks using instructions.
Why do decoder-only LLMs have been slow to adopt for text embedding tasks according to the paper?
Decoder-only LLMs have been slow to adopt for text embedding tasks according to the paper because of their causal attention mechanism, which inherently limits their ability to produce rich contextualized representations. This limitation arises from the fact that at any given layer, causal attention restricts token interactions, influencing the representation of a token solely based on preceding tokens. While this mechanism is necessary for generative capabilities, it is suboptimal for text embeddings, as it hinders the representations from capturing information across the entire input sequence. This architectural constraint makes it challenging for decoder-only LLMs to effectively encode semantic content in vector representations for tasks like semantic textual similarity, information retrieval, and clustering. The paper suggests that this limitation has led to a slow adoption of decoder-only LLMs for text embedding tasks, as the models struggle to produce comprehensive contextualized representations needed for various natural language processing tasks.
What are the three main steps involved in the LLM2Vec approach?
The three main steps involved in the LLM2Vec approach are 1. Enabling bidirectional attention. This step replaces the causal attention mask of decoder-only LLMs with an all-ones matrix, allowing each token access to every other token in the sequence, converting it into a bidirectional LLM. 2. Masked next token prediction, MNTP. This step involves training the model to predict masked tokens based on past and future context, where the loss is computed based on the logits obtained from the token representation at the previous position, not the masked position itself. 3. Unsupervised contrastive learning, CSSSE. This step involves passing an input sequence through the model twice with independently sampled dropout masks to create two different representations for the same sequence. The model is then trained to maximize the similarity between these two representations, while minimizing the similarity with representations of other sequences in the batch.
How does the MNTP step in LLM2Vec differ from traditional masked language modeling?
The MNTP step in LLM2Vec differs from traditional masked language modeling in the way it trains the model to predict masked tokens. In MNTP, a fraction of input tokens are masked, and the model is trained to predict these masked tokens based on the past and future context. Crucially, when predicting a masked token at position I, the loss is computed based on the logits obtained from the token representation at the previous position I1, not the masked position itself. This approach ensures that the model is aware of its bidirectional attention and learns to incorporate information from both past and future tokens when predicting masked tokens. Traditional masked language modeling, on the other hand, typically focuses on predicting the masked tokens directly without explicitly considering the bidirectional context. By incorporating bidirectional attention awareness into the training objective, the MNTP step in LLM2Vec helps the model capture richer contextual information and improve sequence representations compared to traditional masked language modeling methods.
What are the advantages of using decoder-only LLMs over encoder-only models according to the paper?
Decoder-only LLMs offer several advantages over encoder-only models, as highlighted in the paper. Firstly, during pre-training, decoder-only LLMs learn from all input tokens, making them much more sample-efficient compared to encoder-only models, which typically only learn from a small percentage of tokens. This increased efficiency is beneficial when training models with the same amount of data. Secondly, decoder-only LLMs benefit from a rich ecosystem with extensive tooling and well-tested pre-training recipes, leading to continuous improvement by the community. Thirdly, recent advancements in instruction fine-tuning and learning from human preferences have shown that decoder-only LLMs excel at instruction following, making them ideal for building universal text embedding models that generalize across various tasks using instructions. Additionally, decoder-only LLMs have been demonstrated to outperform strong encoder-only models by a large margin on word-level tasks, showcasing their effectiveness in producing rich contextualized token representations. Finally, decoder-only LLMs, when transformed using approaches like LLM2Vec, have been shown to set new state-of-the-art performance for unsupervised models on benchmarks like the Massive Text Embeddings Benchmark, MTEB, further emphasizing their superiority over encoder-only models in certain contexts.
How does enabling bidirectional attention impact the performance of the models in the paper?
Enabling bidirectional attention impacts the performance of the models in the paper differently, depending on the model architecture. For most models, simply enabling bidirectional attention without further adaptation decreases embedding performance. However, for Mistral 7b, enabling bidirectional attention hurts performance much less compared to other models like SLLaMA 1, 3b, and LLaMA 2-7b. In fact, for Mistral 7b, bidirectional connections even improve performance in tasks like named entity recognition (NER) by 0.06%. This suggests that Mistral 7b may have been pre-trained with some form of bidirectional attention, such as prefix language modeling, which could explain its unique behavior with bidirectional attention. Overall, the impact of enabling bidirectional attention on model performance varies across different decoder-only LLMs, with Mistral 7b showing the most resilience to this architectural change compared to other models in the study.
What is the significance of the CSSSE step in the LLM2Vec approach?
The significance of the CSSSE step in the LLM2Vec approach is crucial as it addresses the limitation of decoder-only LLMs in capturing the context of the entire input sequence for sequence-level tasks. While the first two steps of LLM2Vec, enabling bidirectional attention and masked next token prediction, focus on transforming decoder-only LLMs into effective word-level text encoders, the CSSSE step enhances the model's ability to construct meaningful sequence representations. By applying unsupervised contrastive learning via CSSSE, the model is trained to maximize the similarity between two independently sampled representations of the same sequence, while minimizing the similarity with representations of other sequences in the batch. This step ensures that the model can capture the context of the entire sequence and not just individual tokens, making it more suitable for sequence-level tasks. Additionally, CSSSE does not require paired data and can be applied using any collection of sequences, making it a versatile and effective technique for improving the performance of decoder-only LLMs in capturing rich contextual information for sequence representations.
How does the performance of Mistral 7b differ from SLLaMA 1.3b and LLaMA 2-7b in terms of bidirectional attention?
The performance of Mistral 7b differs from SLLaMA 1.3b and LLaMA 2-7b in terms of bidirectional attention in the context of the LLM2Vec approach. Specifically, enabling bidirectional attention without any training hurts the embedding performance for most models, including SLLM 1.3b and Llama 2-7b. However, for Mistral 7b, enabling bidirectional attention has a less detrimental effect on performance compared to the other models. In fact, for Mistral 7b, bidirectional connections even lead to an improvement in performance for named entity recognition (NER) by 0.6%. This indicates that Mistral 7b is more robust to the naive application of bidirectional attention without additional training compared to SLLM 1.3b and Llama 2-7b.
What are the results of the evaluation on word-level tasks for the LLM2Vec transformed models compared to the encoder-only baseline?
The results of the evaluation on word-level tasks for the LLM2Vec transformed models compared to the encoder-only baseline show that constructing token representations with causal attention already outperforms the encoder-only baseline on each of the three tasks: chunking, named entity recognition, and part-of-speech tagging. Enabling bidirectional attention without any training significantly hurts performance for most models. However, further adapting the models via masked next token prediction (MNTP) improves performance for all models and tasks. Specifically, in the chunking task, there are improvements for SLLM 1.3b by 5%, Llama 2-7b by 4%, and Mistral 7b by 4%. Interestingly, combining MNTP with unsupervised contrastive learning, CSSSE, performs worse than just applying MNTP for word-level tasks, as CSSSE is more beneficial for sequence-level tasks.
How does the LLM2Vec approach perform on the Massive Text Embedding Benchmark, MTEB, compared to other methods?
The LLM2Vec approach performs exceptionally well on the Massive Text Embedding Benchmark, MTEB, compared to other methods. Specifically, when applying LLM2Vec to decoder-only LLMs, it leads to significant improvements in performance on the MTEB tasks. By enabling bidirectional attention, adapting via masked next token prediction (MNTP), and applying unsupervised contrastive learning (CSSSE), LLM2Vec transforms decoder-only LLMs into strong text embedding models. This transformation results in a considerable boost in performance for all three models, SLLM 1.3b, Llama 2-7b, and Mistral 7b, on the MTEB tasks. The addition of CSSSE further enhances the performance of the models, with Mistral 7b achieving a state-of-the-art score of 56.80 on the MTEB, surpassing other unsupervised models. Overall, the results demonstrate that LLM2Vec is successful at outperforming previous unsupervised approaches on the challenging MTEB leaderboard, showcasing its effectiveness in producing strong text embeddings for a variety of tasks.